This is lecture 24. In the last lecture, we finished the slides discussing IPC of the synchronous type. So, inter-process communication of synchronous type, be it blocking or non-blocking. What now remains is to discuss asynchronous IPC, but what we're going to discuss for IPC, it applies in general for any type of communication. So we're going to do it once for IPC, but it's going to apply for doing, for example, network communication and so forth. So it's a very powerful and also a useful programming technique. So what is this part called asynchronous IPC? So let's go away from the slides. So a proper term is asynchronous IPC with callback function. This is perhaps the most generic term that we can use. There will be different terms that people may apply. This is a kind of a common way of denoting what we're going to be discussing. So, what is the motivation of this? The idea is that app programmers, so the operating system is trying to support app programmers and make their life easier and more productive. And one of the interfaces that an app programmer is used to or will expect from a modern operating system is precisely this asynchronous IPC with callback function in general, not just IPC, but asynchronous communication with callback function. So let's take an example of an app program. So suppose that on a single host, so suppose that we have a CPU and it runs on some PC, suppose, or laptop, it doesn't matter. And suppose an app is being built that is going to checkpoint. So it's going to back up the files that belong to the different file systems on this particular machine. So suppose it's a backup type of app. And the app programmer codes the backup for this or that reason as a single threaded app, so one process. It's actually going to be one process plus one process, so it's going to be two processes. Yeah. Again, this can be done in different ways. This is just one example to illustrate what the meaning of this is. So, suppose the app looks like this. So it's coded in C, and it has a main function, and this is the overall structure. And what does this function do? It has the main piece of code here. It's main code, which is going to be doing the backup. So therefore, for each file, of course, this has to be written as code. It's going to then, for each file in the system, it's going to create backup copy somewhere. So that's the logic. And if a given file system is large, this will take a long time. So this may take a long while. But this is what this backup app is essentially about, to make copies of the files on a particular file system. And we haven't yet discussed how file systems are architected in OS. That's going to be our last main topic of the course. Now, suppose that you may want the application, this backup app, to be able to be interrupted. So, sometimes you are now starting the backup, but you need to use your PC for some other purpose and you don't want this guy to eat up your CPU cycles, etc. You want to play a game or do something else. And so you want your backup app to be able to cease for a while and then resume when you are ready to do so. One way that you could do it is you could have, so this is running as say process P1, and now you create another process P2, and its code, let me show this in green. So this is the code of this P2 guy. So there's this guy here, which is this, and then there's a companion process. Both are part of the same app called P2. And what P2 does is you may be able to say, hey, P1, cease your operation of creating a backup, but back up the current file and then stop. So you don't want this guy, while it's backing up a file in the middle of the file, just suddenly terminate, which may create junk. So you want this guy to back up the current file, but then not go back to the loop to then go to the next file, so that you have the previous backups that are nicely done, and then later on you can continue and then do the backup of the remaining files. That's the idea. And the way that you as the user communicate to P1 is you're going to use another process P2. It has some GUI probably, and then you click on the mouse, that is, you use the mouse to click on some button, or you type in some command, and it's going to use IPC. So P2 is going to communicate with P1, and P2 is going to send a message to P1 saying, stop now. That is, after you save the current file, don't go to the next file. So this is IPC. We are going to now make two processes communicate for this particular purpose. When this guy is going to be the receiver, the reader, and this guy is going to be the sender, obviously, then when we are using blocking, synchronous blocking IPC, as we discussed just earlier, synchronous blocking IPC, then it would make a blocking read call. So it blocks on read in case a message from P2 arrives. But of course, that doesn't work in this program structure, which is the code of P1, because in P1's code, its main work is to do this stuff. It cannot here make a blocking read call, obviously, because it will hang here and never get to this. The purpose of this process P1 is to loop over all the files and then create backup copies. So this is its main chore. But at the same time, we want the ability for this other process that's part of the same app, when triggered by the user, to be able to send a control message telling this guy, hey, stop doing the backup after you checkpoint the current file and then cease. So now we have this dilemma that this guy needs to be able to read a message that's going to be sent by P2. When a message will be sent, P1 cannot know, or if ever, because P2 may, that is, the user may just let this guy continue until it has checkpointed the last file, in which case there will be no message that is going to be forthcoming from P2 to P1. So a message may never arrive. If a message arrives, it's all up to the user when the user decides to stop this backup process. So when a message arrives is non-deterministic. We don't know. So that's the dilemma. So this code P1 is being coded as one process. This guy is another process. And P1 has this dual task of doing its main work of creating a backup, while at the same time it needs to be able to monitor if a message will be sent from P2 to P1, which then instructs P1 to cease. So how are we going to reconcile these two jobs? We can certainly not use synchronous blocking IPC nor synchronous non-blocking IPC. It doesn't matter. We cannot use synchronous IPC to satisfy this particular requirement. There are different techniques by which apps can be built to make this work. One of them is going to be asynchronous IPC with callback function. So how does a programmer using a kernel that provides this support, so Linux, Windows, they all provide some form of this so that the app programmer can build such apps, which are very common apps. This is just one example. It can be this or that, a web browser that is trying to not use too many threads will also face this issue where a browser sends a request to a server, but then it's not going to block on receiving the response from the server because the browser is needing to get further input from the user, because on modern browser you can click on this link, and while that data is being fetched, you can click on some other link. So therefore, in all of these setups, this problem is a central issue that an app programmer has to be able to resolve and implement. And so with that motivation in mind, so how would one then code P1's app? So in this current approach, the app code of P1 that does the actual backup. So it's a main coded in C. Before it enters into the main work, which is for each file backup each file, all the files. That's the main code. It's going to tell the kernel that when a message from a process such as P2 arrives, then take care of it by running some function that I provide. So this is called registering a callback function. And from our system programming, you will know that in the context of Linux, Unix, etc., these are called signal handlers. So this term callback function is more common in Windows. Callback function. It's a term that's more popularly used in Windows, but it's fairly direct and nice. Signal handlers are a bit sort of more specialized in a way because they talk about signals. They're a very powerful device, but for us, both of them mean the same thing. So a callback function for Linux or Unix would be a signal handler. In Windows terminology, it would just be called a callback function. So there has to be a step before the main code runs where the app program of P1 makes a system call to register, to talk to the kernel and tell the kernel, here is a function. And this is a user function. So this is a function that the app programmer wrote, and it provides a pointer to this function and says, run this function for me if certain event occurs. So in our case, the certain event that is supposed to occur or may not occur is a message arrival from some other process, in our case from P2. That's our event. So this message arrival, this guy, so this message arrival is our event, our future event. We don't know when, we don't know if, but if a message does arrive destined for P1, hence IPC from another process, then we are asking through a system call, that's this step, the kernel to execute a function on our behalf, a callback function or a signal handler using Linux terminology. Hence, we need to provide a function pointer. So for example, using Linux as an example, we would use the signal system call, and then in the case of a message arrival, the event is called SIG.io or SIG.poll. They are the same thing. And then we provide a function pointer. I'll be very explicit by putting the ampersand here, which is of course not needed for function pointers, and say my handler. Of course, we have to check that this went through, but this would be an example of registering a callback function. Which callback function? This guy. So that when this event, SIG.io, meaning a message arrives from some other process to me, and me means P1, then kernel, please run this function for me. And what is this function? Of course, you need to provide the code, the app programmer. So the app programmer provides or codes this piece of code, which is the main piece of code, and then it has to provide this function code. So, of course, it has some types. I'm skipping all of that. It has arguments, skipping all of that. And it's going to now the user, the programmer, is going to code this function main and then this function my handler. And what does this code do? Just what I said, which is this code runs if a message is sent from P2. And there could be different messages, but suppose that if a message arrives, it means now please stop the backup process. So in that case, this guy might set or this guy will first read the message. So there's a read operation, and then if it doesn't need to check what the message is because the message itself is the message, then in that case this could set some global variable, say stop to 1, and stop has been here initialized to be 0 somewhere. And inside this loop, it checks if stop equals to 0, then do this. But if stop is not equal to 0, so it's equals to 1, then stop the checking process and exit after the current file has been completely saved. Some such structure. So this piece of code, also user code, is quite simple. It reads a message because it's IPC sent from P2, and then it's going to, in this example, set some global variable, and then this guy is done. It returns. And after it returns, this guy picks up where it left off, and then in the next iteration, it checks again the stop variable, this global, and this global variable now has changed to 1. Who changed it to 1? Nowhere in this code, in the actual code, is this guy being touched, except for here and here in terms of comparison. This code is being touched by this guy, by this function. But note, no function calls my handler. This guy is not called by any other function. It's not like there's a function ABC, and then inside ABC we'll call my handler. That would be the normal sequence of things. This is asynchronous. So this function is not called by some other function that this guy codes. Instead, this guy tells the kernel this function is to be run on this guy's behalf when this future event occurs. That's it, if it occurs. And that's the contract. So this way of programming is very common, it is very popular, and a kernel needs to be able to support this type of applications by providing system calls like signal, sig action, etc., that then a programmer can use to build such applications. This just being one example. Okay, so far so good. Well, there is a technical challenge in making this work. And the technical challenge is, so here let's draw our usual picture of user mode, kernel mode, and then upper half, lower half, and then of course here in between is our scheduler. And in our context, we're talking about IPC, and in the last lecture, we talked about two processes talking to each other. Say here, this is P1 in the earlier example, here is P2. And in IPC, in our case, only the upper half needs to get involved for the reasons that we discussed last time. So, P2 now, P1, this guy in its main, before it does its main work, which is actual backup, it's going to register a signal handler. So let me just continue to use this example, signal, sig.io, this is the event, and then here is the function pointer, my handler. So this is the key element that's being done. And then stop is set to 0 somewhere, so this has been initialized, and then this code, as I noted, when it runs. And when does it run? If this event happens. When does this event happen? If a message is being sent from P2 to P1, which means that P2 needs to make a system call to send a message. So sending a message. Here is the code of the system call. And this code of the system call is now doing the work that we are needing to here discuss. In our Galileo backends with one CPU, obviously, if P2 is running, P1 is not running because there's only one CPU in this example. So P2 is sending now a message to P1 as we discussed last time. But P1 did this and set things up for a synchronous IPC, which says, hey kernel, hey Xenu, run my handler when a message arrives, in this case from P2. So of course now it's easy to just make this work for this code, for the send system call inside the upper half. It could check, did receiver P1 register a callback function for message receive? If it's no, then there's nothing more to do. But if it's yes, that is, this P1 guy made a system call earlier and registered a callback function, this guy called my handler, to be run by the kernel when this event occurs. So if it's yes, and it knows that it's yes because inside some kernel tables, these kind of notes are of course made when the system call is executed, is called by P1. So if the answer is yes, then because the kernel has this function pointer, it's easy for the kernel in kernel mode to call my handler. This is not a big deal. This is a function pointer. It's just a value that then can be used as the argument of call to jump to this guy and execute it. Of course, the problem here is this is a system call, so therefore we are in kernel mode. And from this system call, it's no problem to make a call to this handler, but of course this would be a violation of isolation protection. Huge violation. Why? Because of the fact that you would be running user code, because this is user code. This is code that the programmer of this process P1 coded. It can be any code. It can be buggy. It can be even malware. Obviously, you cannot jump while you are in kernel mode to user code. That is, of course, nonsensical because it defeats isolation protection. So although it's a simple matter to just call this function, because we have the function pointer that we got passed earlier through the system call, we cannot do that because we are in kernel mode. This function, which belongs to this process, no function of this process calls this code, but still nonetheless, this callback function is part and parcel of this app, P1. So the proper time for this callback function, my handler, to run is 1 back in user mode, because it's user code. We can never run user code in kernel mode. Secondly, in whose context? In the context of process P1, because this callback function is a part of this application, which is now running as a running program called P1. So in our uniprocessor setup, but this can be easily extended to 2 CPUs, etc. So it's important here just to make everything concrete for 1 CPU. So P2 now is running. That's why it's making a system call to send a message to P1. So P2 is running, but P2 has switched from user mode to kernel mode. I'm talking about Linux, Windows, etc. In Xeno, of course, we are always in kernel mode, but we are always thinking in terms of a modern operating system and then changing Xeno to make it more up to date. So P2 is running. It makes a system call to send a message to P1. It's now in kernel mode. It's running this upper half code. This upper half code performs this check. It notices, oh yes, the receiver has registered a callback function for a message receive. So now it's this guy's job to make that work. How? To arrange things, to arrange this function, my handler, this user code, to be executed in user mode, obviously, and in the context of process P1. The current process is P2, the sender. So this guy, P1, was context switched out. And at some point, the scheduler will decide, hey, P2, you get to run on the CPU next. So the easiest, the most straightforward way to arrange this handler, this callback function, to be executed, to be run is when the app process to whom this handler belongs, because it's this handler who registered, it's this code, the code of P1, that made a system call earlier on to arrange for the kernel to know this function pointer and the event upon which to execute it. So when P1, which is now not current, becomes current in the future, we want P1 not to go back to where it was and pick up where it left off. That would be the normal case. Instead, we want P1 to make a detour. So we want to arrange things that when P1 becomes current, it performs a detour. Detour how? It doesn't jump back to the instruction that P1 should execute next before it was context switched out. Instead, it should jump to, so P1, when it is context switched in, should make a detour to this function. And this function is part of this app. It's now going to run in user mode because this guy is being context switched in. It's back in user mode. It's perfectly appropriate to run this user code, which this guy or a person or folks wrote. And if this has a bug, well, it's okay. P1 may crash, but that's always a possibility. The rest of the system is protected from any bad behavior by this function. The only one who suffers is the application to whom this function belongs to, which is, of course, the very objective of isolation protection. Protect the rest of the system. If an app crashes because there's a bug there or some malware, that's the app's business. It's not the kernel's business. The kernel's role is to protect all other processes and the system from misbehaving apps, including just regular bugs. And because this is now being arranged to be jumped to when P1 resumes execution by being context switched in, but rather than P1 jumping back to where it was earlier, it makes a detour and jumps to my handler. And when my handler is done, because it's a function, so there's an AND. When this guy is done, then this guy jumps to where P1 would have originally jumped back to. That's why this is a detour. So again, at runtime, so all of this is done not statically prior by compiling. These are all runtime techniques, runtime software engineering techniques. Very, very powerful and useful. So here you see the types of stuff that you've practiced in the first three labs being utilized for supporting asynchronous IPC using callback function. So again, we want to run this thing in user mode because it's user code. Under whose name? In the context of the process P1 to whom this function belongs to. Very natural setup. When is a good time for both of these conditions to be true? When the app process to whom this function belongs to is scheduled next to run, it becomes current. Instead of jumping to the next instruction here before it was context switched out, we are going to make a detour and jump to this callback function. And when this guy is done, then this guy jumps, this guy returns to the original return address that P1 would have jumped back to when it goes back to, so P1 goes back to user mode and P1 ran earlier, it slept or it did something that caused it to be context switched out. Maybe it used up all of its time slots. Whatever the case is, to that next instruction is where my handler would jump to. So how do you make that work? It's the same technique that you've practiced so far, which is you are going to manipulate the runtime stack. So here is the stack of P1. That's the runtime stack. Let's use Xeno as our concrete example because you are practicing in terms of kernel programming for this specific platform to make everything concrete. P1 was context switched out. We know that in context switch, we saved P1 state by pushing it onto the stack. That means EBP, eFlags, and 8 general purpose registers, as we know. And then the top of the stack, that was saved in the process table, the saved stack pointer field of the process table entry. So now, when P1, so this is when it was context switched out. At a future time, it's going to be context switched back in. Context switch in. So out, in. So when that happens, of course, pop, 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 with the subtleties that we discussed earlier to restore the registers. And then context switch would typically, unless it's just been created, but in our scenario, it ran earlier. So therefore, context switch would return to resketch, and then resketch would return to whoever called resketch. But what we want to make sure is this guy, this callback function, my handler, needs to satisfy 2 requirements to preserve isolation protection. It must run in user mode, and it must run in the context of the process that registered it, so in the context of process P1. That's the most natural condition. In Xenu, of course, we always run in kernel mode, but we know where the separation of user mode, kernel mode is. You even implemented trap system calls in Xenu for 2 or 3 system calls, and you actually performed a trap. The only thing that you did not do was start off a process in user mode and then change to kernel mode and then back to that, but it was purely correct trapping. So you know how to do that, and you know where the boundary is. You know the system call wrapper, etc. So you know the 3 software layers and all of this stuff. So that's all part of the background to understand what's going to happen here. So now in user mode, when are we going to be in user mode if this were Linux or Windows? Of course, we're going to use Xenu, but there's a boundary that corresponds to Xenu, which corresponds to Linux and Windows. So what is that boundary? If it was a system call like sleep that caused the scheduler to be called, then resketch returns to sleep, which is a system call. And this guy returns to whoever called sleep, say main. So now in this setup, where is a correct meaning, or where is a correct interpretation of what user mode is in Xenu, where we are always running in kernel mode? Well, there's a natural place. This is all kernel code. Because this is, of course, the system call, which is part of the upper half. So when this guy returns, so this guy executes its read instruction, that's when we are crossing the boundary from kernel code to user code. In Linux, Windows, it would be from kernel mode to user mode. So it's the sleep MS guy that is the boundary. Its return is the boundary between kernel mode, kernel code, user mode, user code. In Xenu, it would be always kernel code, and in this case, user code, because we are always in kernel mode in Xenu. That is what this thing here would mean in user mode. That means to make a detour means what? That somewhere here, is the stack frame of SleepMS. And as part of the stack frame of SleepMS, a key piece of information, of course, is the return address that's been pushed, that then SleepMS uses to jump back to whoever called SleepMS at the next instruction. In this case, say main. But we want to make a detour, and we want to make this address here be the address of the callback function, myHandler. So we're going to again, at runtime, go into the runtime stack, make modifications at runtime to force the software to behave in a manner in which it was originally not designed to do. Of course, the app programmer is asking the kernel for all of this to happen. So in that sense, yes, it was designed to make all of this detour possible. But it's not in the conventional sense where a function calls another function, calls another function. That's the easy stuff. This is the more subtle part where by manipulating the stack and the return address here in particular, we would change this return address in the stack frame of SleepMS to now contain myHandler's address. And when myHandler runs, it's going to have its stack frame here. So its stack frame is then going to be somewhere here. I'm not going to mess things up by trying to draw it here, but when this guy jumps, then this guy uses so when this guy jumps, it's going to now do its thing, its code, and then at the end it has to return. It has to jump. And where is it going to jump to? To this original return address. So we are needing to save it somehow, and we are going to set up this stack so that after all is said and done, we're able to achieve this detour operation. And it's all made possible by using the techniques that you have already learned step by step during the labs. So that's something that you will encounter in lab 4. Very, very important programming technique. So this is an overview of what asynchronous IPC with callback function is. It's a very powerful technique. So keep in mind what this entails and its connection to isolation protection. If you did not have to worry about isolation protection, then of course everything is much, much, much simpler. But this is, as we have seen, an essential service that modern kernels in general provide. It's absolutely needed that we make sure that isolation protection is always preserved. So this myHandler, this user code, must run in user mode in the context of the app process that registered this handler, which technically means in this string of events, we need to manipulate the return addresses, which live, of course, inside the stack of this process, so that we are able to run this handler in user mode in the context of P1. And then after this guy is done, the process goes back to where it was and picks up where it left off. So the execution of this handler is completely asynchronous. There's no fixed timing that we know when this will happen. When it happens, then we are forcing this sequence of events to occur to satisfy these two properties for isolation protection. All right, so that is our discussion of asynchronous IPC with callback function. Now we will branch back to the slides and discuss process synchronization, coordination. They mean the same thing. So we are back in our slides. It's somewhere here. The exact location is not that critical. So far we have been able to make processes talk to each other synchronously or asynchronously. Two main mechanisms. Now what we are going to do is we are going to allow processes to coexist and not get into each other's way. So if, for example, and this is the key element, if processes are sharing data structures, so that's the key practical concern. So two or more processes sharing data structures, common data structures. So they are sharing data structures that reside in memory, and there's process P5, process P6, and maybe other processes that read write to this shared data structure. And the scheduler, we don't know when this guy will run, when this guy will run, when some other guy will run. No matter when which process runs, we want to ensure that this shared data structure does not get corrupted. It is not corrupted. That is, it doesn't undergo changes that are not intentional. So all of this has to undergo orderly access. Orderly access by two or more processes that are sharing data structures. That's going to be the main concern of synchronization or coordination of processes, which we are discussing here. So with that in mind, let's go down. Two approaches. So what we will be talking about here, the slides, read through the bullets, but the key point is we are going to make this coordination, synchronization work using two different techniques. One is hardware support. So this is a common theme that you can now see throughout the course, and the other one is software support. So here we are going to make this work mainly using software support. Mainly doesn't mean it's solely, it means mainly, principally, it's going to be using a software means. And by software means, what we mean is using semaphores. But there are hardware primitives that we can use to make the same thing happen as well. And as you can imagine, there are always advantages, pros, and cons to both. In general, we would like to use software support because it's gentler, it is less drastic, it is less disruptive to the system. But for some things, this is better suited, and even for this, we need to make use of this to make it work for most cases. So we need to understand both of these methodologies. The two main applications of what we're going to discuss is mutual exclusion, this guy, and producer-consumer interaction, this guy. Both are very, very commonly used in software applications, including kernels. But it's not just for kernel. These are very, very common primitives that software engineers use. Of course, we are going to focus mainly when it's used inside the kernel, but the same setup applies in user space. So what is mutual exclusion? It means here is some shared data structure, as I said. And as the word indicates, suppose there are two processes, P1 and P2, who are sharing it. It means that when P1 is accessing, P2 cannot access. and vice versa. If P1 is accessing, then P2 cannot access. It's mutually, so the data structure can be accessed only in a mutually exclusive manner. So that's the idea here. So in another way, this data structure itself is kind of atomic. If we are casting this in the context of databases, then there we don't use the term processes. It's a more generalized notion of a procedure called transactions. So you have a transaction T1 that begins and ends, and here is its work. Here is another transaction that begins here, and here is the code, and it ends. And these two transactions, like P1, P2, are sharing a common data structure. And here, a key requirement in general is that this transaction will appear to be atomic to other transactions. So while this is going on, this transaction cannot squeeze in and then mess up the shared data structure. Now, how this is done efficiently is a fairly sophisticated matter, and we are not going to discuss this matter here. But this is when you're using databases as the setup, the same exact scenario as what we're discussing here will happen, will occur with mutual exclusion. Producer-consumer interaction is a special case of this, where the data structure is a queue. So it's a queue, and we've seen queues before, and we're going to consider a FIFO queue, as we've also seen before. So to this FIFO queue, there is a process P1 that writes to the queue. So this is the writer, the sender. There's a guy that reads from the queue. This is, say, P2. This is the reader. So there are two processes, one acting as a writer and one acting as a reader. And this is, of course, the shared data structure. So the shared data structure is not arbitrary. It's a specific shared data structure, which happens to be, in our case, a FIFO queue. And when this shared data structure is of this specific form, then it lends itself to using a technique, that's what this guy is about, that allows this shared data structure to be orderly accessed without this atomic locking of the entire data structure. So in general, if you don't have extra properties, then you may have to just lock this entire thing, let this guy use it, unlock it, then let this guy use it. Of course, this guy locks it before it uses it. So that's called mutual exclusion. Here it's general. We don't know what this data structure is. However, if this data structure is this FIFO queue, and in this case one writer, this writer is called a producer because it produces stuff. That's why it's called producer-consumer. Consumer is the guy who reads, who consumes data. So this is the reader. Consumer is the reader. So you can say writer-reader interaction, but more popularly we just use the term producer-consumer interaction. And this is a FIFO queue. And now you can imagine if this guy is writing somewhere here, and this guy is reading from here, and there's a gap between here and there, then this guy can happily go on reading from here, and this guy can happily go on writing to here, and there's going to be no interference because these two things have a gap in them. Because it's FIFO, it means this guy is reading from the end. This is the oldest piece of data, and then it moves this head in this direction. The writer has written this much, and then this is free space. So this gap is free unused space, and if it writes, if it produces more stuff, it's going to, of course, add it like so. And as you can now imagine, this is a circular buffer. It wraps around. So if this is a byte, the next byte, it doesn't fall off, it's this guy. It's a circular buffer, so it's a donut. So what we have here is, when we are building these apps, then as you should know what a circular buffer is, but I'm here just pointing it out again so that we're all on the same page. This is a FIFO queue. You are now going to write here, and you may fill it up. And if it's full, and this is full because no one has read it, then there's no more space to write to. But you have now written up until here. But there's a reader. So this is the writer. But then there's a reader who comes along and reads from the oldest data. That's the oldest data. It's a FIFO queue. And so now the reader reads, so it clears them because it becomes empty. All the stuff that it has read is cleared up, it's deleted. So the more a reader reads, the more empty space, free buffer space, of course, arises. So that when the writer here tries to write the next bit or byte, it doesn't fall off the cliff. Rather, this continues. The next byte here is actually this byte, this free element. And so this buffer should be drawn not like a line, but like a donut. Here's our donut. Here is, if this is an array, then this is index 0, index 1, index 2, and suppose the array is of size 100. So there are 100 elements. So it's array 0, 1, and 99. That's our circular buffer. And suppose it's of type char, so it contains 1 byte. So 0, 1, 2, 3, 4, etc. And then what comes here? The last guy here is 99. The previous guy is 98. And so after 99, we are back to 0. That's what we call a circular buffer. And when we talk about producer-consumer queue, we always mean in this context that we have a circular buffer on which we then have to maintain pointers. And as long as these pointers don't clash, because there is this gap in between, then the writer, which is a process P1, the reader, which is a process P2, they can operate on the shared data structure at the same time without getting into each other's way. But when these pointers come close, which means that there is no free gap in between, then we have a clash. So that's what we have to be very careful about. So going back to our slides, the two main applications of interest here are, again, these two. Going downwards, it explains what this is. Just read through it. And here is the canonical example of what producer-consumer interaction is. So we'll pick up from here next time.